This is an example for design of normal concrete mix, and this is the mix design form for the DOE method, Department of Environment. In this flowchart procedure, there are 5 stages. This is the first stage. The first stage is to determine the free water semen ratio. The second stage is to determine the free water content, unit in kilogram per meter cube. The third stage is to determine the semen content and the unit in kilogram per meter cube. The fourth stage is to determine the total aggregate of the mix design and the unit in kilogram per meter cube. And the last stage, the fifth stage, is to determine the percentage of total aggregate content for fine aggregate and also coarse aggregate in kilogram per meter cubic. So let's go to the example. And this is the example for the unrestricted design. Given the following requirements, as shown here, the characteristic strength for the compressive strength is 30 Newton per meter square at 28 days with the defective rate 2.5%, and the constant K for the defective rate 2.5 is 1.96. So in this manual, okay, so the value for the constant K can be determined in part 1, okay, part 1 under the background information. And the type of the Portland cement used in the mix design is 42.5. The slump required is to 10 to 330 millimeter. The maximum aggregate size is 20. Maximum free water semen ratio is 0.55, and the minimum semen content is 290 kilogram per cubic meter. So a maximum semen content is not specified, so there is no data for the maximum semen content. There are no previous control data, and thus a standard deviation of 8 Newton per millimeter square. The fine and coarse aggregate to be used are uncrushed. The relative density is unknown and is assumed to be 2.6. And the fine aggregate has 70% passing 60 micrometer sieve. And this is the chart and table to be used in this mix design. So the first one is to determine the free water semen ratio. So under the stage 1, first the item 1.1 is the characteristic strength. So in the requirement given in the question, the strength at 28 days is 30 Newton per millimeter square. Okay, so this is 30 Newton per millimeter square at 28 days, and we insert this data in the mix design form. 30 Newton per millimeter square at 28 days. And the proportion defective, okay, given in the question is 2.5%. And this is the defective rate given, okay, for the K of 1.96. Next is the standard deviation. Okay, standard deviation. from figure 3, either we have the data or no data. Then if we refer back to the question, so stated here, there are no previous control data and thus a standard deviation of 8 Newton per millimeter square is used. And we note here 8 Newton per millimeter square. Just in case if we do not have this data, we can refer to figure 3. And this is figure 3. Figure 3 is the relationship between standard deviation and characteristic strength. So the characteristic strength is 30. Okay, and let's say our result is less than 20 result, and we bring this up, and then our standard deviation is 8. So next data is to calculate this value, okay, to calculate the margin. And our margin here is for proportion defective 2.5, our K is 1.96, and based on equation C1, as stated in this manual, equation C1 is K multiplied with S, where K is the constant value 1.96 multiplied with the standard deviation given for K 1.96, and K for 0.196, okay, the K is 2.5% defective. And we go back to this equation, thus 1.96 multiplied with 2.5, okay, this 2.5 proportion defective, okay, sorry, multiply with the standard deviation, which is 8, and the answer here is 16, or margin is specified. In our case, the margin is not specified. You need to calculate this using equation C1, so here is dash. The next is to calculate the target mean strength. Target mean strength is referred to equation C2 in the manual. And this is the equation C2, where the target mean strength is Fc plus M. The characteristic strength 30 megapascal plus 16. Okay. So we need to plus the characteristic strength here, which is 30, plus the margin here is 16, and our target mean strength for this MIG design at 28 days is 46. Next is 1.5, the Semen strength class as specified in the question is 42.5. Both is the type 1 Semen, ordinary Portland Semen. The difference is the 552.5 is for the early strength. Okay, 42.5 is for the normal hydration. Okay, and next is 1.6, the aggregate type, cost and fine. As stated in this data, okay, in the question, our maximum fine, our fine and cost aggregates to be used uncrushed is uncrushed. So both is uncrushed. This is uncrushed, so we circle the uncrushed. Okay, either you circle or you cross this crush. Okay, and free water semen ratio based on this data is determined using table 2 and figure 4. First, we look at table 2. Data from table 2 is bring to figure 4, and this is table 2. you can find this table in the manual. Okay, so this is table 2. The semen class is 42.5. The type of coarse aggregate is uncrushed, and the compressive strength is at 28 days. Okay, and data we need to carry to the figure 2 is 42. So we bring this to figure 2. Okay, my mistake, sorry, figure 4. Okay, figure 4 sebelah sini je, figure 4. Okay, so this is figure 4. Okay, relationship between compressive strength and free water semen ratio. So from this figure, we can determine the free water semen ratio. So starting line using data from table 2. So this is data from table 2. Table 2, we obtain the data at 28 days is 42. Okay, 42, this is 40. This is compressive strength. This is compressive strength. Compressive strength, compressive strength. So we use this axis. 40 to 50, 42 is around here. Okay, around here. Then we draw the similar line with the nearest line. Okay, this line is similar to the nearest line. Okay, this line. Okay, this line. Okay, we draw this. Okay, and next, after this, okay, we refer back to our table. Okay, from the target mean strength, our target mean strength is 46. Okay, so we bring this value to figure 4. And this is again the figure 4, 46. 46 is this around here. Okay, let's say this is 46. Okay, take straight line to the right. This is 46. This is 42 from table 2. Okay, and draw the straight line down. Bring this point here. So the free water semen ratio for 30 megapascal at 28 days, the characteristic strength, and also for the target mean strength 46, our free water semen ratio is around 0.47. Okay, 0.47. And then we state 0.47 in 1.7. So this is the maximum free water semen ratio if specified. Okay, in the question it is specified the maximum free water semen ratio is 0.55. so it is specified the maximum free water ratio is 0.55. so this is the maximum. So which one you need to select? Okay, based this one use the lower value, thus we select 0.47, okay, as our free water semen ratio for this mixed design. So the summarize of the stage 1 is recorded in this table, okay, in this rectangular shape. Okay, 0.47. Next is the stage 2. Stage 2 is to determine the free water content. Okay, unit in kilogram per meter cube. Okay, so our VB slump, our slump is suggested the range between 30 to 30 mm. Okay, as given in the question. So this is 10 to 30 mm, the slump required, and our maximum aggregate size is 20 mm. The maximum aggregate size is 20 mm. So no data for VB. This is VB or VB time. We have no data for the VB time. So our slump, the proposed slump is range between 10 to 30 millimeter. The maximum aggregate size is 20, and thus free water content is determined from table 3. Okay, this is table 3. Okay, table 3, our slump. Okay, our slump is this range. and the maximum aggregate size is 20, and our coarse aggregate is uncrushed. Okay, so we bring this to the, okay, so the approximate free water content is around 160, okay, unit in kilogram per meter cubic. Okay, right here 160. So this is the summary for the stage 2. Okay. So next stage is stage 3 is to determine the semen content. Semen content is from equation C3. So if you didn't look at C3, you can also calculate this by the understanding that W over C equal to water semen ratio. So our W over C is 0.47. Our water semen ratio is 0.47. Just in case the fundamental is the same. Okay, the equation fundamental is the same. Okay, so our water semen ratio is 0.47. The free water content is 60 here. So meaning 160 divided by C equal to 0.47. Okay, thus here is 160 divided by, this is divided by 0.47, then we get C. And our C here is around 340 kilogram per meter cube. And no maximum semen content stated in the question, but there is minimum semen content stated in the question, which is 290 kilogram per meter cube. Okay, this is the data for the minimum semen content. Okay, based on this, okay, use 3.1, here is 3.1, 3.2, 3.3. So now we have 3.3 and 3.1, 3.3 and 3.1. Use 3.3 if this value is larger than this value. Use this value, use minimum semen content if minimum semen content value is more than the semen content obtained from equation C3. But in our case, the semen content here is more than the minimum semen content. Thus, our summary for the stage 3 is 340 kilogram per meter cube. So this is free water semen ratio, the modified. So our case is unrestricted result. Okay, so this is, you can learn this in concrete technology, okay, in year 4. Okay, next is the stage 4. Stage 4 is to determine the total aggregate content in the mixed design. Our relative density, okay, there are two, either known or assumed. Okay, in the question, the relative density is unknown and is assumed to be 2.6. 2.6, and the fine aggregate has 70% passing 60 micrometer. So we use these two data to determine the sand and also coarse aggregate. Okay, so as given in the question, we assume our SSD, relative density of aggregate. This aggregate is under the SSD condition. Okay, is 2.6. Okay, we assume. And the concrete density based on the figure 5. Okay, we look at the figure 5. Okay, this is figure 5. Okay, so we want to know the wet density here. Okay, so this the X line is the free water content. Here is the free water content. Okay, the free water content. So in stage 2, we determine that our free water content is 160. Okay, and we assume that our the relative density is 2.6. So we bring this 160 up and stop at this point, and bring this line, straight line, to the left. And our concrete density is 2,400, the wet density of concrete. Okay, thus the concrete density based on figure 5 is 2,400 kilogram per meter cubic. And then we can determine the total aggregate of the content in the mixed design. Okay, if I erase this one, okay, we know that, let's say this is the concrete and this is the aggregate. Okay, and this is the cement, around 340 cement. And here is water. The density, the volume is around, the density is around 160. So this is one concrete mixed design, and this is aggregate. This aggregate, the C4 from the equation C4. This is the C4. The equation C4 is total aggregate content is the wet density, which is 2,400, minus the cement content 340, and also minus the free water content 160. Then we can get the total aggregate content. Okay, so this total concrete, one whole concrete here, one whole concrete here is 2,400. To get this amount is 2,400 minus cement, 340 minus water content, and the answer is 1,900. So next we go to the stage 5. Stage 5 is to know the proportion of the fine aggregate and the coarse aggregate from this 1,900. So 5.1, the grading of fine aggregate, as stated in the question, it 70% past the 600 micrometer sieve. And then for the figure 6, we determine the proportion of fine aggregate. Okay, the fine aggregate, the sand. Let's look to the figure 6. And this is figure 6. The proportion of fine aggregate according to the percentage passing of 600 micrometer sieve. So here there are 3 graphs. Okay, the first graph is for the maximum aggregate size 10 mm. The second graph is for the maximum aggregate size 20 mm. And the third graph is for the maximum aggregate size 40 mm. In our case, our maximum aggregate size is 20. Then we select this graph. We use this graph. Okay, so in previous assumption, we use our slump range between 10 to 30 millimeter. So thus we will proceed our proportion of fine aggregate with this graph. Okay, this graph. Our free water cement ratio, is 0.47. So let's say here is 0.5. 0.4, 0.5, 0.6, and zero 0.7 is around here. Let's say around here. And the percentage passing 600 micrometer sieve is 70%. So here is 60 and 80. So we draw 70% value in between 60 and 80, and we bring this up, stop at this new red line and bring this value to the left. Thus, this is our proportion of fine aggregate in percent. So it ranged between 20 to 30%. So let's say we take 27%. We take 27%. And we proceed here. The proportion of fine aggregate is 27%. Thus, we know that the fine aggregate is by using equation C5, and this is the equation C5. The fine aggregate is calculated by total aggregate content 1900 multiply with the proportion of fines, which is 27%. Meanwhile, for the cost aggregate is the total aggregate content minus result from this equation. Okay. So in other words, if we bring this out, okay, here is the aggregate, and the content of this aggregate is 1900, and 27% of the 1900 is the fine aggregate. Thus, the equation is 1900, okay, times 27%, and the content of the fine aggregate in this mixed design is around 151. Okay, so 27%, so the answer is 151. So 151 from 1900 is the cent, and other than this is the cost aggregate content. Thus, this equation for the cost aggregate content 1900 minus 515, then we get here 1385. And this is the summary for the fine aggregate and cost aggregate content in stage 5. Next, we summarize all our finding in each stages into this per meter cubic to the nearest 5 kg. Okay, look up the semen. Okay, this is the semen, and semen is determined in the stage 3. Our summary is 340. We get 340 here. Okay, here is 340. The water is 160 to the nearest 5 kg. So the fine aggregate is 515, and cost aggregate is 138, but we know our maximum is 20 mm, thus it contains the combination of 20 and 10 millimeter. Then we go back to the DOE manual. Okay, this is the ratio for the combination for 10 mm, 20 mm. The second ratio here is for combination 10, 20 and 40 mm. In our case, we have combination of 10 and 20 mm. Thus, the ratio is 1/2. Meaning, 1 part for 10 millimeter and 2 part for 20 millimeter. Okay, and the total cost aggregate is 1385. Thus, we get here 1385 divided by 3. So we bring one portion as the 10 millimeter and the two portion as 20 millimeter. Thus, we get here to the nearest 50 kg is 460 here, and here is 925. Okay, 925. So let's say here, if you get here the semen content 342. Okay, let's say 342, and when we want to bring this value into this per meter cube to the nearest 5 kg, Thus, we look at this nearest 5 kg, and the answer for the semen is 340. Okay, so if here is 344, thus the value here is 345. Okay, then we calculate the per trial mix of let's say 0.05 cubic meter. Okay, then 340, this 340 multiply with 0.05, thus we get in kg 17 kilogram for semen. 160 multiply with 0.05 for water in kg is 18.0. So the same process for the aggregate, the same formula. 515 multiply with 0.05, so we get here is 25.7, and here is 23 for the coarse aggregate with diameter 10 mm, and the 20 mm is around 46.2. Okay, so we know that this okay, so this unit is in kilogram per meter cube. So we need unit in kilogram, okay, to proceed to the mix design in the laboratory, and we can weighing the material in kg. Okay, thus we need to eliminate the cubic meter. So cubic meter is based on your specimen to be cast. Okay, so here is, for example, 0.05 cubic meter. So you multiply with this value, multiply with this meter cubic. So thus we get material in unit kilogram. That's all for this example. Thank you.